Welcome everyone to our YouTube series, Test Prep Made Easy. So in this particular series, we are going to post regularly questions on our YouTube channel. The questions may pertain to CAT preparation, maybe pertaining to GMAT preparation, as well as of various topics which are tested in these particular exams. For example, Quants, LRDI, English, and various areas which are tested. And each day we will handle certain number of questions and their video solutions. The best approach is to these questions in these videos. So have a happy preparation ahead and enjoy the video. Thank you.
All right, so these are the questions that we are going to try in today's video. If you have tried it already from the thumbnail, good enough. If you haven't, you can pause the video at this point and try it once before you look into the solutions. We recommend you doing that. But if you just want to enjoy the solution, that's also good enough. And go ahead and watch the solutions now. All right, so here we have a question which is actually an application of stars and bars algorithm. So I'll just give you the basic idea. I'll not explain how it comes out to be. I do explain that in our classes, but that will take a longer video for this. So if you have n identical items which needs to be distributed to R boxes. By the way, when we say boxes, implicitly they are always distinct boxes. So when you distribute n identical items into R boxes, the number of ways you can do that without any restriction is n plus R minus 1 C R minus 1. So these are the number of ways you can distribute n identical items into R boxes. So we can actually apply this idea in this question. Because if you look at the question, it says in how many ways can 8 chocolates. So whenever it says 8 chocolates, until unless it has been mentioned different types of chocolates, you assume that all the chocolates are identical any which way. So items of the same type are always identical to each other until unless explicitly mentioned. So there are these 8 chocolates who have to be distributed, which have to be distributed among 3 kids in such a way that each kid gets at least 1 chocolate, but none of them get more than 4 chocolates. So these are the 2 constraints that we have. For instance, any kid, so each kid should have at least 1 and at most 4. That is what the question says, right? So each kid can have 1 to 4 chocolates. If you remember this definition that I mentioned earlier, n plus R minus 1 CR minus 1, this is without any restriction. So you have to always understand how to apply it. So don't mug up any extra formulas for this. This is the advantage if you can smartly deduce whatever is required as per the question itself. So for example, in this case, so what I'm going to do is I'm going to assume the 3 kids to be A, B, and C. And I know that they have to be distributed 8 chocolates. So I'm just going to begin with A plus B plus C equal to 8 because the total number of chocolates with the kids will be always 8, right? Now, first of all, about the allocation. So there is a minimum allocation, that is each kid should have at least 1 chocolate, right? So let me put a box for each of the kid here. And let me distribute 1 chocolate to each of the kid to begin with, because they're identical chocolates. It really doesn't matter. So now what we have is we have a transposition of the same equation. So so what I mean to say is, so from this 8 chocolates, I'm just taking off 1 chocolate for each of this kid. And we will be left with 5 chocolates, right? So this equation now converts to something like this. Now, the maximum thing that we have, we can handle that in a different way. So let's just carry on and solve this question and you'll understand what I'm doing. So first thing, I'm going to figure out the number of distribution for this. And this is as good as distributing n identical items, so the 5 chocolates into 3 boxes, which is the R boxes. So that can be done in 5 plus 3 minus 1, C 3 minus 1, which is 7C2 or 21 ways. You can quickly calculate that. So we have 7C2 or 21 ways of distributing these many chocolates. So that is the 5 remaining chocolates. But this is again without restriction, right? But we have to take an additional restriction into account, which is each kid should have been ensured that, it should have been ensured that no kid gets more than 4 chocolates, right? Please remember this initial allocation out here. So we already had allocated one chocolate to each of the person or each of the kid out here. If over and above that, I distribute 4 chocolates or 5 chocolates to any one person, so that person will have more than 4 chocolates, right? So for example, out of these distribution, think about a distribution like this. So suppose A gets 4 chocolates out of this 5, B gets 1, and C gets 0. So A already had 1 chocolate, he gets 4 more chocolates, so gets a total of 5 chocolates, right? B is not a problem, C is not a problem, but A cannot have more than 4 chocolates. That is what the question has told us, right? So we have to take that into account. And how do we do that? A very simple way to do this. First of all, think about A being equal to 4 plus x. So what I'm trying to do is I'm trying to find the this is something which I call as call the tipping point, the point at which the problem starts happening. So we already have 1 chocolate. If I distribute 4 more chocolate, then it's an issue, right? So I'm just going to distribute or represent A with 4 plus some other variable. It doesn't matter what variable you take. So let me just rewrite this. So we have 4 plus x plus b plus c is equal to 5, right? Now, all of these distributions, if you think about it, so suppose I put x equal to 0. So A already has 1 chocolate and then gets 4 plus 0, that is 4 chocolates. So 1 plus 4, 5. So that is not allowed. If x is 1, so this becomes 5. A already had 1 chocolate. So again, A gets 6 chocolates, which is also not allowed. So any value of x I put, that is not allowed, right? So I'm going to remove those cases. So this is what I'm going to solve for. So by the way, this transposes to something like this: x plus b plus c is equal to 1. You don't have to apply n plus r minus 1 cr minus 1 here. It's a very simple thing. This 1 can go to either x or b or c. So there are 3 cases, right? So there are 3 cases where a is 4 plus x. But please understand, this is where I've taken a as 4 plus x. So I can also have something like b as 4 plus x, right? So I could very well have b as 4 plus x. Same problem, right? Over and above 1 chocolate which is already distributed to b, you cannot give 4 or more chocolates, right? So even if this would have remained as a, and this would have been 4 plus x, you'll find there's a symmetry out here, right? This will also have 3 solutions. The one will go to either a or x or c. So effectively what I'm trying to say is, this substitution that I did in the previous case, so if you just don't have to do this every time, so if you just consider any one of the variables, so that is a in this instance, as long as there's a symmetry. So by symmetry I mean this thing happens each kid. So each kid you have the same kind of constraint happening, so you don't have to worry too much into it, and you would not have too much problematic or complicated questions coming in CAT or relevant exams where you need to apply this more in a more detailed manner. So that is never going to happen. So in this case, you can just consider the symmetry here. So if A has 3 distributions which is not allowed, B should also have 3 distributions which are not allowed, C should also have 3 distributions which are not allowed. So effectively you will have 3 into 3, which are 9 distribution which will be not allowed. So just exclude those from the earlier 21 cases you obtained, and you'll simply get the answer. So the answer will be 21 minus 9, which is 12, or option A in this case. So this is the fastest way. The explanation bit, I had to explain a lot of basics. If you don't know that, if you do know that, this is a very strong formula. It helps us in a lot of different types of problems. even dice problems, questions. This has huge usages. I've explained in our class a lot of different variations based on this type of idea. So yeah, so that's all I had to add for this particular question. I hope everything was understood. Thank you. All right, so we are looking for how many even natural numbers. Do not miss even natural numbers out here. I mean, even, don't miss it out. From 49 to 201 are divisible by neither 7 nor by 9. So what are we actually looking for? So try to understand the question or the constraints out here. So first of all, we're looking in the range of 49 to 201, both inclusive when it says from to. So in this range, we are looking for multiples of 2, but that is even number, but not multiples of 7 and not multiples of 9. So this is what we are looking for, right? So we will think in terms of even numbers only, but among that, we are going to exclude certain numbers which are multiples of 7 or multiples of 9 or both. So that is something which is going to be our working approach. So let us first figure out all the multiples of 2. So very simple. You can just check this out. I mean, there are a lot of different ways to do this. But from 1 to 201, there are 100 multiples of 2, which is up to 200, by the way. And from 1 to 48, by the way, we have to consider from 49 to 201. It will not be a problem in this case because 49 is anyhow not a multiple of 2. But anyhow, the correct way. 1 to 48, there are 24 multiples of 2. So just subtract these two. So you have 100 minus 24, basically 76 multiples of 2, right? So you have total of 76 multiples of 2. Now, among them, there are some multiples of 7 as well. Now, please understand, if it is a multiple of 2 and a multiple of 7, so please understand we are now into the set of numbers which are multiples of 2. So basically what I've done is, I have taken a universal set which are multiples of 2 from 49 to 201. So I'm considering these set of numbers only, and there are 76 such numbers. So the universal set is from these 76 numbers only. So among them, we have to think about multiples of 7 and multiples of 9, and then we are going to ignore these and consider all the numbers which are outside this region, something like that. So I'll just put in the values here itself. So let's say multiples of 7 and multiples of 9. These are what the circles are indicating. So let me calculate here and put the values here. So let's look at that. So first of all, among the multiples of 2, those which are multiples of 7, so implying multiples of 14, right? So let's do the same approach that we did here. So 1 to 201, the number of multiples of 14. Simple enough, 201 by 14. Just think about the quotient out here, that's all. So 14 times 1 is 14, and then you have 61 left out, so that will be 4 more. So there are 14 multiples in this range. If you know 14 square is 196, then your life becomes a little easy. 1 to 48, again same idea, 48 divided by 14. So that is just 3 multiples, right? I mean, 42 is 14 into 3, or you can just divide this. So you have 14 by 3. You can just one other thing you can do is you can reduce both the numerator and denominator. If 48 by 14 is you're finding it tough, you can do 24 by 7, same thing. So 14 and 3, so there are 11 multiples of 7 among these multiples of 2. So this entire circle, comprise of 11 numbers. So let me just write this for the circle. So there are a total of 11 numbers in the circle, right? Let's do the same thing for the multiples of 9. By the way, let me just take this off as well. So maybe I have a bit of space to work with this. So let me just quickly expand this entire thing. Right. So I've just written this so that it's visible to you properly. Okay. So now we are concerned with multiples of 9, but again among multiples of 2. So basically what we are looking for is multiples of 2 and multiples of 9, right? So same idea. they have to be multiples of 18, right? So again, let's do the same thing. So 1 to 201, we have a total of 201 by 18. That is the number of multiples of 18. By the way, 180, if you know, I mean, you should know 180 is a multiple of 18 any which way. Just add 18 to it, you get 198, right? So it should be 11 times. So basically, you have 11 multiples in this range. And 1 to 48, you have 48 by 18. Just reduce the numerator denominator. You get 24 by 9, which is 2. So you get 11 minus 2, which is 9 multiples of 18, right? And that is multiples of 9 in this case. So 9 multiples out here. So this circle is indicating 9 numbers. So that much is done. And now finally, there will be certain numbers as well, which are common to both of these, right? So common to both 7 and 9. But again, do not forget the sample space or the universal set is among the multiples of 2. So those which are falling here, those numbers which fall here are actually multiples of 2, multiples of 7, and multiples of 9, right? So effectively multiples of 126, which is the LCM of 279, in this case product as well, but ideally, I mean conceptually, that is the LCM of 27 and 9. So multiples of 126. Now, by the way, in this case, this is simple enough. I mean, you don't have to do the same thing that we have been doing. You can quickly find that 1 to 48, obviously there will not be any multiples of 126, right? Until 201, you just get 126. I mean, 126 into 2 is itself greater than 201. So there will be just one number, which is a multiple of 126. So this region is indicating one number. And now just look at the circle. So since this is 11, so this has to be 10. And this circle is indicating 9 numbers. So this has to be 8 numbers here, right? So we have a total of 19 numbers out here. So 10 plus 1 plus 8, all that's all I'm doing. But if you remember, there are a total of 76 numbers from which we have to exclude these numbers because we are supposed to count which are not multiples of 7 and not multiples of 9. So 76 minus 19, and that is 57 as our final answer. So option A. Pretty straightforward question. I mean, ideas based on this have appeared in CAT a lot of times. I mean, even in CAT 2020, I think there was a question based on this idea. So pretty straightforward question. I hope everybody is aware of this idea. There's nothing too much to it, just basic counting on the basis of certain conditions, multiples of this, multiples of that, and so on. So yeah, that's all I had to add for this question. Hopefully everything was understood. Thank you for joining in. Okay, we have the set of numbers from 1 to 25. Now we need to find the number of ways we can select 3 elements or 3 numbers from this set such that the sum of the 3 elements is always divisible by 3. I don't get the context of writing always in this case, but anyhow, so we're looking to select 3 elements from this set so that the sum of the 3 elements is divisible by 3. That is what the question is, right? So in this kind of cases, always try to do this beforehand. So if you think about any number for that matter, when divided by 3, it will have a remainder of 0, 1, or 2, right? So any number can actually be represented in 3 forms, either 3k or 3k plus 1 or 3k plus 2, where k is a certain integer, a natural number, to be a little more precise in this context. So 3k is basically those numbers which are multiples of 3. 3k plus 1 implies that when you divide by 3, the remainder is 1, right? K is the quotient. Similarly, 3k plus 2 are indicating all those numbers which are giving a remainder of 2 when divided by 3. And now just group how many numbers are of each form. So for example, in this case, if you in this case, what I typically do is I look for the highest when it starts with 1, of course. So I look for the highest multiple of 3 that I have. So the highest multiple of 3 that I have is 24. So I look for 1 to 24. So 1 to 24, I'll have 8 numbers of each type, right? From 1 to 24. But that 25 is of this form, isn't it? So 25 when divided by 3 leaves a remainder of 1. So if I consider 1 to 25, all that happens is, I mean, we get extra 1 number in this group. So this is what we have, right? So from 1 to 25, these are the numbers. So from 1 to 25, let me just convert this from any number. So from 1 to 25, or in the set A, that is, these are the types of numbers that we have. So 3K types are 8 numbers, 3K plus 1, 9 numbers, and 3K plus 2, 8 numbers. Now, think about how do you add 3 numbers to get a multiple of 3. So this is case based. I mean, you have to consider this in this particular scenario. Don't overcomplicate in these kind of cases. Keep it simple and just take case based. It's not very tough to do. I'm just going to show you how to avoid mistakes. So that is what my target will be. So I always start with 3Ks, all the 3Ks that I can take. So I can take 3 numbers of 3K type. I can do that, right? So if I take three numbers of 3K type, each of them are multiples of 3. So 3K plus 3K plus 3K. You can just imagine. Forget the K. I mean, you can, if you have to write that correctly, then you can indicate that as 3K1 plus 3K2 plus 3K3. I mean, that is fine. But I'm saying this is just for your own understanding, right? So imagine it as 3K plus 3K plus 3K. So obviously it is a multiple of 3, right? So 3 numbers of 3K type will definitely satisfy the condition, right? Now, if I consider 2 numbers of the type 3K, then I have to take one more number of either of these 2 types, right? Now, this should naturally occur to you. These 2 numbers that you have considered of 3K type, you cannot, when those 2 are added, they are giving us a multiple of 3 themselves, right? So 3K plus 3K. Now to that, if you add a 3K plus 1 or a 3K plus 2, it really doesn't matter. You'll always have a certain remainder left out when you divide by 3. So you can never have a multiple of 3 when you add 2 numbers of type 3K with one number of either 3K plus 1 type or 3K plus 2 type. So this is not going to give you a sum which is a multiple of 3. So this is not going to work. So this is a cross. So I'll just take this off just to avoid too much of cumbersome this thing. Let us consider one number of type 3K. Now this is interesting. So if I do take one number of type 3K, then I can actually take one number of 3K plus 1 and one number of type 3K plus 2 to get a multiple of 3K. Just notice these two. Forget about this. I mean, this 3K is irrelevant actually. So when I have one number of 3K, the other 2 numbers that I pick up, one number of 3K plus 1 type and one number of 3K plus 2 type, just add these two. Are you not getting a multiple of 3? 3K plus 1 and 3K plus 2. So that is giving me a multiple of 3, right? Again, if you have to do it technically correct, you can also do something like this. It really doesn't matter. See, these two are anyhow multiple of 3 and 1 plus 2 is a multiple of 3, right? So obviously, I mean, these two things taken along with one number of type 3K will definitely work. But what I can't do is, I mean, if I take one number of 3K type, I cannot take 2 numbers of the same type, that is 3K plus 1 or 2 numbers of 3K plus 2. This is not going to work. Just check it out. So one number of 3K, if you take 2 numbers of 3K plus 1, then those two added will be 3K plus 2 type, isn't it? So added to a 3K is not going to give us a multiple of 3. That will leave a remainder of 2. Similarly, if you add 2 numbers of 3K plus 2 types, so that will be 3K plus 4, right? And 4 divided by 3 leaves a remainder of 1. So it is leaving a remainder. Forget about what the remainder is, but it is not a multiple of 3. Focus on that part. So effectively, one number of 3K taken, you have to take one number of type 3K plus 1 and one number of type 3K plus 2. So this works, but this is what you have to do, right? And finally, if you don't take any 3Ks, so if you do not take any 3Ks, so that is no, or let me not write that. So basically just remember this. So no 3K taken. How do you take 3 numbers from here and then produce a multiple of 3? See, if I take 3 numbers of the type 3K plus 1, just focus on the remainder, 1 plus 1 plus 1. So that adds up to a multiple of 3, right? So this will work out. Similarly, if I take all the 3 numbers of the type 3K plus 2, then 2 plus 2 plus 2 is also adding up to a multiple of 3. So that also works out. So I can actually take all the 3 numbers of the same type, either of 3K plus 1 or of 3K plus 2. So that I can definitely do, right? But what I can't do is I cannot take 2 numbers of 3K plus 1 and one number of 3K plus 2 type. Check this out. You have the remainders 1, 1 and 2. Added is 4. That is not a multiple of 3. I can't even, take two multiple or two numbers of 3k plus 2 type and one number of 3k plus 1 type, and 2 plus 2 plus 1 is 5. It's not a multiple of 3. So if I have to, take, uh, three numbers without taking any 3k types, then all the three numbers should be of the type 3k plus 1, or all of them have to be of the type 3k plus 2. Very similar to this one, right? When you took three numbers of 3k. So all of these are allowed. So now coming to the counting part. So these are the cases. You always have to consider this depending on how many numbers you have to take. For this particular scenario, these are the cases that we have to consider. And now the counting part. So the counting part is just application of NCR, because we are selecting, not arranging anywhere. Three numbers of 3k will be selected from these 8 numbers that is available to us. So three numbers selected from 8, so that is 8C3. 8C3 is, by the way, 8 into 7 into 6 by 1 into 2 into 3. This goes off, so you have 56. So 8C3 is 56. So just keep that in mind, because that will be useful here as well. So let's check that out as well. So here also we are taking three numbers from 8 numbers, which is also 8C3. So that will also be 56. Three numbers of 3k plus 1. Let us quickly do this to begin with. So 3k plus 1, there are 9 numbers actually. So this will not be 8C3, this will be 9C3. So that will be 9 into 8 into 7 upon 1 into 2 into 3. This goes off with 3 and this goes off with 4. So 3 into 4 is 12, into 7 is 84. So you have 84 as this. And one number of each of these type, right? So one number of 3k is 8C1. One number of 3k plus 1 from 9 numbers. So correspondingly, by the way, 9C1. And then another 8C1. So 8 into 8 is 64. Or what you can do is 8 into 8, leave it. So yeah, that is 8 square. And then you have this 3 square. 9 is 3 square, right? So 8 square into 3 square is 24 square. And if you know 24 square is 576, so that will help you directly in this context. So these are all the cases. So you need to add them up. So you have 56 plus 576 plus 84 plus 56. So no tricks will work. I do observe that the last digit is 2, but there are a couple of options in last digit of 2, and then we have none of these as well. So you have to actually calculate this. So no worries. If you add these two, by the way, just shift the 4 to here. So you get 80 plus 60, which is 140. When you add 56 and 576, if you are good with it, just convert or remove 24 from here and add here. So you get a 600 here. And because you removed the 24, you're left with 32, right? So 32 plus 600 is 632. So if you add these two, you get a total of 772, which is option C. So that's the answer for this question. Hopefully everything was understood. I just wanted to explain through the basics itself. There is nothing to be marked up in this type of question. You just have to take the cases and figure it out. If you do get a question like this in an exam, you should understand one thing. This should be a big takeaway from this particular video explanation. If you have a question like this, you have an experience now that when you have to count 3 elements adding up to a multiple of 3, that will take a bit of time, right? You have to take the cases into consideration. You have to then figure out for each case. You have to do that carefully, not rush into it. So my suggestion, if you're good with these kind of things, then mark it for review, even if you are good at these things. So don't solve it in the first go. Just finish off all the questions which you can solve quickly. I mean, quicker than this. There will be a lot of questions which you can actually solve quicker than this for any exam for that matter. Just do that and then come back to this question. If you are attempting a paper which is adaptive in nature, so something like GMAT or NMAT, then you don't have an option. But if it is an adaptive paper, then a question like this will appear in a very later stage, because this will be something time consuming when they set up the difficulty level and something anything related to that. That is done in a long run basis. So that will automatically, I mean, this question will automatically have a higher rating, because a lot of people will mess up or maybe leave this question, mark it randomly. So that will automatically increase the level of this question. So don't have to worry in that case also. But if you have an option of scanning in a paper, then do scan, leave this question as marked for review or something, and then maybe come back later on and solve this question. So yeah, that's all I had to add for this problem. I hope everything was understood. Thank you for joining. Okay, this is a very interesting question. So we have to find the number of rational numbers. By the way, I hope everybody is aware of what is a rational number. A rational number is anything which can be presented in the form integer by integer. Obviously, the denominator has to be not equal to 0. That is a silly thing to remember. But yeah, I mean, it has to be it should be a number which can be always represented in the form some integer by integer. So something which can be represented fractionally. That is a rational number. So find the number of rational numbers where a is a fraction. Okay, this is a proper fraction, by the way, lying between 0 and 1. So effectively, so let me just do this. So we are trying to find a which is of the form p by q, where p and q are obviously integers because it has to be a rational number, and importantly p has to be less than q. Because we are looking for a proper fraction, like lying between 0 and 1. P cannot be greater than or even equal to q. So P has to be less than q, such that when A is written as a fraction in the lowest form, the numerator and denominator add up to 500. This is a very good question, actually. So numerator and denominator is P and Q, by the way. So P plus Q adds up to 500. Now, please understand, this is a relevant thing. A is written as a fraction in the lowest form. So we have to consider this as the lowest form, this P by Q. What it means to say is, so suppose I have something like 4 by 496. Although out here, yes, you can argue that 4 and 496 are adding up to 500, but this is not the reduced form, isn't it? So we can actually reduce this to 1 by 249. So this can actually can be reduced further. Now you don't have these two adding up to 500 anymore, right? So what did I do, by the way? My bad. Anyhow, so that is 500. So 1 by 124, yeah. I halved it once. Anyhow, so but I hope you get my point. So these two added do not add to 500 now in the lowest form. So in the lowest form, it has to add up to 500. So how do you tackle that? So the idea is something like this. Obviously, this P and Q should add up to 500. So we have to take numbers which do that. Additionally, there should not be anything common between P and Q, any common factor, right? So P and Q, this is what are known as co-prime or relative prime. So there should not be any common prime factor, or very simply put, uh, let me write that as well. The definition of this. So when two numbers are co-prime to each other, the understanding is the HCF of P and Q should be 1. I hope everybody is aware of HCF. So there should not be any common prime factor between these two numbers, this numerator and denominator. So this is what we are looking for, right? Now, there are a lot of different ways to apply this, or solve this question. This is a type of question which has a specific way to actually solve this. So until unless you're aware of that way, you would not be able to solve this. I can't go into too much details of the basics behind it. I would discuss the idea here. In our classes, we do explain all the relevant roots of it, so origin of it. I mean, how do you get that, so that we don't have to mug it up. But unfortunately, I cannot do that in this video. So I'm going to explain this till to a point where you should be able to understand what is happening. So first of all, let me take some examples out here. So let's take 1 plus 499. This works out. Let's take 2 plus 498. Notice that this doesn't work out. 2 and 498 are not co-prime to each other. Their HCF is not 1, right? So 2 and 498 is not working out. Let me take 3 plus 497. You'll see that these two are actually co-prime. So this works out. 4 plus 496. This is the example I took earlier. This doesn't work out. Even 5 plus 495 doesn't work out, right? Notice the examples in which they are working out and they are not working out. Let's do that. Let me just take one arbitrary one as well, or maybe I'll do that later on to explain this further. So notice something. If one is co-prime to 500, so this 500 is the grand total out here. So if 1 and 500 are co-prime to each other, then this 1 and 499 are also co-prime to each other. Similarly, if 2 and 500 are not co-prime to each other, so 2 is actually a factor of 500, right? So if 2 and 500 are not co-prime to each other, So then this 2 and 498 are also not co-prime to each other. If you check this 4, the 4 is also, I mean, in this case, again, a factor of 500. But in that case, you can see that 4 and 496 are not co-prime to each other, right? 3 on the other example, on the other hand, 3 is not, 3 is actually co-prime to 500, right? So there is no common prime factor. If you want to do this a little fast, so what you can do is you can just write 500 in the factorized form. I hope everybody is aware of this. So this is 2 square into 5 cube. So wherever there's a 2 or a 5 or any combination of 2 or 5, it will not be a fact, or it will not be co-prime to 500, right? So 3 has nothing to do with 2 or 5. 3 is a different prime. So if I take another example for that, let's say something like, so I'm going to take some arbitrary examples now. So let's say 35. Now 35 is actually 7 into 5. Now 5 is actually a factor of 500, right? So there is a prime factor 5 in 500. So 7 is not a problem, but 5 is a problem. So 35 plus whatever you can see to add 500, you will have these two numbers not co-prime to each other. So what will happen is, again, reiterating, so when you represent 35 by 465, this will not be the lowest form. So it will reduce to something. And when it reduces to whatever, I'm always thinking this total to be 1000. Anyhow, so you have 7 by 93. So in that case, here you can see that these two are not adding to 500 anymore. Same reason, right? I mean, that's not the reduced form. So on the other hand, let me take another example. So let's take 143. Now 143 is not a prime, it's 11 into 13. But 11 and 13 has nothing to do with this 500, right? 500 has prime factors 2 and 5 only. So if you take 143, what added to 143 will give us 500. So 143 plus 357 will add up to 500, isn't it? Now notice, because 143 and 500 had nothing in common, I mean, no prime factor in common. So 143 and 357 automatically becomes co-prime to each other. So this is a general logic here. I mean, very basic understanding. If A and B has any common factor, that common factor will be a factor of A plus B as well. So this is the idea that we use in this type of problem. But as I said, I mean, I'm not going to go too much into it, but this is the basics I hope everybody has understood. So now our job is very easy. So what I'm going to do is, first of all, I'm going to look for all the numbers less than 500 which are co-prime to 500. And there's a very easy way to do that. It is known as the Euler-Tauchian function. So what you do is just take the number 500 and then do this operation for each prime. So what you do is 1 minus 1 by p for each prime factor of this 500. So the prime factors out here are 2 and 5. So just do this operation for each prime. So for 2, you do 1 minus 1 by 2. And for 5, you do 1 minus 1 by 5. So just do this. So you get all the numbers which are less than 500, which are also co-prime to 500. So effectively, that is 500 into half into 4/5, which is nothing but 2/5 of this, or 200 numbers, right? Now, the interesting thing to note here, if there are 200 numbers which are less than 500 and co-prime to 500, now among those 200 numbers, there will be half the numbers which are less than 250, that is half of 500, and half the numbers greater than 250. So the reason is very simple. Just let me show this explicitly. Just check this out. I mean, 1 plus 499, this works out. I'm just going to write few of them which works out. 3 plus 497, 7 plus 493, 11 plus 489. So this goes on. Let's check the point 249 plus 251. Then we have this 251 plus 249. And this goes on till actually 499 plus 1, right? So this entire numbers, I mean, this 1, 3, 7, 11, up to all of this are 200 numbers, right? But what you observe at this stage, I mean, this is just switching over, isn't it? So till this point, you should have 100 numbers here where P is less than Q, right? and then again 100 numbers where P is actually greater than Q, because it's the same number just swapping, right? If you have 1 plus 499 as a solution, then 499 plus 1 is also a solution for this particular thing. So effectively, you should have equal solutions where P is less than Q and equal solutions for where P is greater than Q, right? So effectively, the solutions that satisfy our constraint is half of this 200 or 100 as our final answer. So something a little technical in this particular question. Usually these kind of things are not tested that much in aptitude tests. But in certain exams, I've found in NMAT and SNAP, sometimes these kind of ideas which are tested. But yeah, things are changing nowadays, so there is a less amount of chance that these type of things will come up just because of application of this Euler-Toscan function. So typically you don't have to apply Euler-Toscan function without knowing it, and there are few people who will actually know it until unless you have just mugged it up without understanding it. So that's the entire thing I wanted to add for this problem. If you like numbers and like counting, then this will be a really fun question for you to try. And then hopefully I've got the right answer in that case. It's a very nice question. There are a lot of applications on this idea as well. But yeah, if you have that in future, I hope you can apply this idea that I explained today. So that's it for this problem. I hope everything was understood. Thank you for joining in.
Hopefully you liked the solutions we provided for these questions. And if you did like it, do not forget to like the video and share, subscribe, and comment. Do subscribe to the channel and click on the bell icon. In that case, you'll get notification as soon as we upload a new video. And if you want to check a bouquet of courses that we provide, so we have a huge variant of courses from customizability to full preparation. You can check our website, www.mathoratory.com. I'll leave the link in the description below. And have an enjoyable preparation ahead. Welcome to the Mathoratory family and have a good exam ahead.